The photoelectric effect is the process whereby electrons are ejected from a metal surface when light of suitable frequency is incident on that surface. So we remember that a metal is a substance where all the nuclei are bound together and the electrons are free to move around in what is called a sea of delocalized electrons, which essentially says those electrons are free to move anywhere on that surface, but they would need a certain amount of energy to escape that surface. So until this point, we have viewed light as a wave in the sense of it is able to interfere with itself. We have done a number of experiments in optics in which we showed how light creates an interference pattern. Now what that would suggest is that if a light is shone on a surface for long enough, every single electron would be able to absorb enough energy to escape from the surface of that metal, which would mean that after a long enough period of time, all metals would be left without any electrons. Now, in reality, it's found that this is not the case. It's found that light does not behave like a wave because not all electrons will always be ejected from the surface of a metal. So the other way that we can look at light then is as a stream of particles. We have heard of the wave-particle duality of light, and what this says is that it suggests that instead of the light being a stream or a steady wave that comes out of the light source, what this is now seeing the light as is a stream of particles. We know that each of those particles contains a specific energy, and that energy is a function of the frequency of that light. We remember that h is Planck's constant, and so the energy of any one photon is determined by the product of Planck's constant and the frequency of that light source. Now, the reason why this explanation is considered to be correct is because we know that each electron can only absorb a single photon of light. And if they can only absorb one photon of light, that then explains why the photoelectric effect only occurs at certain times or at certain frequencies. And that is because each metal has a specific amount of energy that is required to release or for an electron to escape. That amount of energy is known as the work function. It is essentially the product of Planck's constant and the threshold frequency for that specific metal. So what that tells us is that in order for an electron to escape this metal surface, the energy of the photon energy, would have to exceed or be greater than the work function for that metal. Now, with this explanation, we find that it makes sense why not all light sources are able to create the photoelectric effect, and that is because they do not necessarily have light of a high enough frequency. And it also explains to us how we can determine how much or how many electrons are able to escape from the surface of that metal. Because there are now three possibilities for the amount of energy that a photon has. We know that if the photon energy is less than the work function for that metal, we know that there is not enough energy for an electron to absorb and escape that metal, so we say that there are no photoelectrons, or the photoelectric effect does not occur. The second option is that if the energy of the photon is equal to the work function, then what that means is it's just enough energy for an electron to absorb and escape from the surface, but not enough energy for it to move away from the surface because it has no additional kinetic energy. And the third option is that the energy of the photon is now greater than the work function, which means that there would be a photoelectron, an electron that escapes, and then the excess energy, the difference between the amount of energy of the photon and the work function, would then become the kinetic energy. And from this we can find the formula, which is our kinetic energy is equal to the energy of the photon minus the work function, this being the amount of energy required to escape, or we can rewrite that as the photon energy is equal to the sum of the work function and the kinetic energy, where we remember kinetic energy is half mass times the velocity squared. Note that this only applies when the energy of the photon exceeds the work function. And just a final note, we know that since the energy of a photon is determined or dependent on the frequency, and we know that light always travels at a constant speed, what that tells us is that there's also a relationship between the energy and the wavelength, which is E is equal to hc over lambda. So often we would refer to the color of light, where we know that color is dependent on the wavelength of that light. There are two changes that we can make to a light source that is resulting in the photoelectric effect. The first one is that we can change the frequency of the light source. And we know that for the photoelectric effect, we see light as a stream of particles called photons. We know that we can determine the energy of a photon by taking the product of Planck's constant and the frequency of that light source. And we know that every single metal has something called a work function, which is the minimum energy required to eject an electron from that surface. And that work function corresponds to something called a threshold frequency. So we know that by changing the frequency of a light source until we get a frequency that exceeds the threshold frequency, at which point electrons are able to absorb a single photon, which gives them enough energy to escape and become a photoelectron. Thereafter, if we continue to increase the frequency, we would add more kinetic energy to those photoelectrons. So the first change we can make to a light source is by changing the frequency. The second change that we can make is to change the intensity. So we see intensity as brightness in light. We say that a very bright light has a very high intensity or high luminous intensity, and what that is scientifically is increasing the number of photons striking an area per second. So instead of there being 10 photons striking an area per second, if we increase the intensity, we could now have 30 photons striking an area per second. So now what we can see here is that this has not changed the energy of an individual photon. The energy of a photon is only ever related to the frequency of that light source. What we have changed, though, is the number of photons that are striking a surface, which means we have changed the number of photons that can be absorbed by electrons. And if the energy of that photon exceeds the work function, what that does is it increases the number of photoelectrons. Because there are more photons striking the surface per second, there are now going to be more photoelectrons leaving the surface. So it's very important to see here that a frequency change affects only the energy of a photoelectron, whether or not it has enough energy to escape, once it can escape, how much kinetic energy it has. Whereas an intensity change affects only the number of photoelectrons. If the photon energy is greater than the work function, then increasing the intensity will increase the number of photoelectrons that are ejected per second. We also know that different colors of light have different wavelengths and therefore frequencies. So often, instead of talking about a frequency change, we will refer to a color change. And then it is important to know that red light with the longest wavelength has the shortest or lowest frequency, and blue light with the shortest wavelength has the highest frequency. Basically saying blue light has more energy. Since blue light has more energy, that means it is more likely to eject photoelectrons, and once more, that energy has nothing to do with the intensity of the light. The intensity only affects the number of photoelectrons that can be ejected. Using the work function for a specific metal, there are a number of calculations that we can do. And so by way of an example, we have here the work function for zinc as 6.9 times 10 to the negative 19 joules. Remember that work function means the minimum energy required to eject an electron from the surface of that metal. Now, the first and most common question here would be to calculate the threshold frequency for that metal. So threshold frequency is the minimum frequency of a photon required to eject an electron, and that is calculated using the formula work function is equal to Planck's constant multiplied by our threshold frequency, where the work function was given to us as 6.9 times 10 to the negative 19. Planck's constant is always given as 6.63 times 10 to the negative 34, and the threshold frequency is our unknown here that we can solve to find the threshold frequency for this metal is 1.04 times 10 to the power of 15 hertz, meaning that is the minimum frequency that a photon must have in order to eject an electron from the surface of this metal. A similar question to this is, instead of asking for the minimum frequency, we can ask for the maximum wavelength. This is possible because frequency and wavelength are inversely proportional to each other, which means that where we have a minimum frequency that can eject a photoelectron, we also would have a maximum wavelength that can eject a photoelectron. And we can calculate that by saying that the speed of light in air is always a constant, 3 times 10 to the 8. The frequency here is the frequency that is our minimum, our threshold frequency that we've already calculated, 1.04 times 10 to the power of 15. And then our maximum wavelength is therefore going to be 2.88 times 10 to the negative 7 meters. A common question that follows this would be something along the lines of calculate the kinetic energy if this metal is radiated with a wavelength of 200 nanometers. And the first thing that we need to see here is we asked for the kinetic energy. We have the work function, so we're going to be looking to use the formula E is equal to work function plus kinetic energy. Now what we need to do is we first need to be able to determine what the energy of this photon is. And we can do that in one of two ways. We can either say that our energy is equal to Planck's constant multiplied by speed of light over the wavelength, or we can do it in two separate steps where we first say we convert our wavelength into a frequency using C is equal to F lambda, and then we use the formula E is equal to Planck's constant multiplied by the frequency. Either one of these would get the correct answer. I prefer to use this formula as it does it in a single step. So inserting the given values, Planck's constant once again is our constant, 6.63 times 10 to the negative 34. Our speed of light, always a constant, 3 times 10 to the 8. And that is divided by the wavelength, which was given as 200 nanometers, where we know nanometers means 10 to the power of negative 9. And so we can then say that the energy of this photon is 9.945 times 10 to the power of negative 19 joules. Note that I have not rounded this to 2 decimal places because it is still within a question. We only round our final answer. Now that I have the energy of a photon, I can go back to the original formula, which says that the energy of a photon, 9.945 times 10 to the power of 19, negative 19, is equal to the work function of this metal, still 6.9 times 10 to the negative 19, plus our kinetic energy. Then with that we can solve to find that the kinetic energy of an ejected photoelectron here is 3.045, or what we can now round to 3.05 times 10 to the negative 19 joules. And this is the energy of an ejected photoelectron. It is also sometimes referred to as the maximum kinetic energy. A common follow-up question would be calculate the velocity of an ejected photoelectron, and we can do that using the formula kinetic energy is equal to 1/2 multiplied by the mass multiplied by the velocity squared. And since we now have the kinetic energy, we have the mass of an electron, a given constant, we can solve to find the velocity of that ejected photoelectron. A common addition to this type of question would be, now what happens if the intensity of this light is increased? And we know that intensity refers to the number of photons, and so increasing the intensity is going to increase the number of photoelectrons that are ejected, whereas the question that asks what happens if we increase the frequency or decrease the wavelength, we know that that is going to have an effect on the energy. Increasing the frequency increases the energy, which is going to increase the amount of kinetic energy that these photoelectrons are ejected with. One of the most common graphs that we come across in the photoelectric effect is the graph of kinetic energy against frequency. And what we can see here is we can see that the graph starts out negative as the frequency increases and then eventually becomes positive and continues to increase with the frequency. Now what's important here is that we can use this formula to determine what the x and y intercepts of this graph mean. And the first one, to determine what the y-intercept of this graph means, we rewrite this formula by saying the energy of the photon is the product of Planck's constant and frequency, and that's equal to the work function plus the kinetic energy. This is the y-intercept, which means at this point the frequency must be equal to 0, which means that 0 is equal to the sum of work function and kinetic energy, which then can be rewritten as the work function is equal to negative kinetic energy. And this is when frequency is 0. So that tells us that the y-intercept on this graph is the negative work function. The second intercept that we would want to find here is the intercept with the x-axis. We know that that is going to happen when the kinetic energy is equal to 0, and we get this by rewriting this equation where the energy of the photon is the product of Planck's constant and frequency. The work function is the product of Planck's constant and the threshold frequency, and in this case the kinetic energy is now 0, and so we can then rewrite this or simplify it. Let me write that or leave that as kinetic energy, which leaves us with h times f is equal to h times f0, which then simply tells us that the frequency at the point where kinetic energy is 0 is our threshold frequency. So what this tells us is that we now have a graph that can tell us where the work function is or what the work function is. It can also tell us what the threshold frequency is, and now this graph makes more sense because it tells us that when the photons have an energy or a frequency less than the threshold frequency, there is no kinetic energy because there are no photoelectrons ejected. We know that once the threshold frequency is surpassed, then the kinetic energy of those photoelectrons increases, and it increases with a steady gradient, and the gradient of that graph is kinetic energy over frequency, which we know then is Planck's constant, a constant value for a constant gradient on that graph. The second common use of the photoelectric effect, or the way that we show it, is in an electric circuit that's set up as follows. We have a battery connected to an ammeter connected to a photocell that we can see here essentially breaks the surface, where we have a metal over here connected to the negative terminal of the battery, and here a metal connected to the positive terminal of the battery. And what we can see here is that by shining a light onto this metal, if the frequency of the light exceeds the threshold frequency, then electrons will be ejected from the surface of this metal and be attracted towards the positive terminal of the battery, which would then register a current on this ammeter. So the first graph that we can draw here is a graph of current versus frequency, and what this shows us is that no current would register until the point where we reach our threshold frequency, and from then onwards a current would register because now electrons are being allowed to bridge that gap, which completes the circuit and allows a current to flow. This circuit can also be used to demonstrate the fact that intensity changes the number of electrons that are ejected, because what we will find here is that if instead of plotting current versus frequency, we now plot current versus intensity, we'll find that as we increase the intensity of this light, we increase the number of electrons that are ejected, and more electrons being ejected means more charge moving across that gap. More charge, we know, would increase the amount of current, because current is the charge over the amount of time. So what we find is that our current versus intensity graph will increase for as long as the intensity increases, again, as long as the frequency exceeds the threshold frequency. So once again, these are two different ways in which we can see the photoelectric effect, but both of them show us the same thing. They say that no photoelectrons are ejected until the threshold frequency is surpassed. They tell us that the kinetic energy increases once the threshold frequency is surpassed, and they tell us that the intensity affects only the number of electrons ejected. It does not affect whether or not an electron is ejected as a photoelectron. We know that the atom consists of a small dense nucleus that contains protons and neutrons at the center, and then the electrons are arranged in energy levels around the center of the atom, or around the nucleus, and they are arranged in order of increasing energy, basically saying that the electrons in the first energy level have the least energy, and then every energy level that you move outward, the energy would increase. Now, since the first energy level has the lowest energy, we often refer to that as the ground state. An electron in the first energy level is in the ground state because it has the lowest possible energy. Now, every different element has different sized gaps between those energy levels, basically saying that for a specific element, the energy required for each energy level is different. So, for example, if we take an arbitrary element and we say that for this element, electrons in the first energy level have 3 joules of energy. Electrons in the second energy level then have 7 joules of energy, and electrons in the third energy level have 15 joules of energy. Obviously, the number of energy levels increases as long as the energy increases. Now, what is possible here is transitions between these energy levels. So the most common transition that we'll find is an electron in the first energy level moving up into the second energy level. Now, as we can see, an electron in the first energy level would have 3 joules of energy. In order for it to move into the second energy level, it would have to gain 4 joules of energy. Once it has done this and moved into a higher energy level, we say that it is now in an excited state. It has moved from the ground state, the lowest possible energy, it has absorbed energy and moved into an excited state. Further excited states are also possible. It is possible for that electron to jump straight from the first to the third energy level, and that would mean it needs to go from 3 to 15 joules, so it would have to gain 12 joules, and still it would then be in an excited state. So as you can see, when electrons absorb energy, they move up an energy level into a more excited state. It is also possible here for an electron in the second energy level to move up to the third energy level. In that case, it would be moving from 7 to 15, so it would be required to absorb 8. And we say once again it is in the excited state. Those are for energy absorptions. The opposite of that is also possible. So once an electron has absorbed energy and moved to an excited state, it is only a matter of time before that electron drops back down into its ground state. And since it required the gaining of 4 joules in order to move up into an excited state, it can now lose those 4 joules when moving down back into its ground state. In the same way, this electron that moved from the second to the third energy level can now move back down. All of these basically in reverse, where a move up an energy level requires an absorption of energy, and moving down an energy level gives off energy or emits energy. So in conclusion, every element has unique energy levels, basically saying that this element may have 3 and 7 for its first two energy levels, another element would have 5 and 12, and so you can tell an element by looking at those energy levels. Secondly, in order for an electron to move up into an excited state, it must absorb energy. And third, when an electron moves down from an excited state back to its original state or back to the ground state, energy must be emitted. We know from the photoelectric effect that light can be treated as a stream of particles, and we know that we can calculate the energy of those particles of light, known as photons, either by knowing the frequency or by knowing the wavelength of that light. We also know that white light is essentially just a mixture of all of the different colors, or all of the different wavelengths, or all of the different frequencies, which essentially says that when white light is passed through a prism, we would be given a continuous spectrum, and the continuous spectrum would look something like this, where we can see that as the wavelength changes, the color of light changes, and the frequency also changes. Now, we know that it's possible for electrons to absorb photons of light, and we also know that different substances have different energy levels, or different energies for their energy levels. So what I've got here is a very simplified idea of white light that is emitting a continuous spectrum of energies. I've just got 1 to 8 joules here, and it is going to pass through two different gases. The first one has its first energy level with an energy of 1 joule, and you can see the energies there. And we know that the photons with the correct amount of energy will be absorbed. So what we can see here is that a transition from the first to the second energy level would require 1 joule of energy. A transition from the first to the third energy level would require 4 joules of energy. A transition from the first to the fourth energy level would then require 8 joules of energy. We know it's also possible for transitions from the second to the third, which would require 3 joules of energy, and the second to the fifth, which would require 7 joules of energy. And the last transition that is possible here would be a transition from the third to the fourth energy level, which would require 4 joules of energy. So what that tells us is if we shine a continuous spectrum of light through this gas, what we will find is that those specific energies will be absorbed. So the 1 joule photon will be absorbed as it passes through. The 3 joule photon will also be absorbed and allow that electron to transition into a higher state. The 4 joule photon will be absorbed, the 7 joule photon will be absorbed, and the 8 joule photon will be absorbed. So the light that we see emerging from the other side is now missing a number of energies, and so we see only a part of that spectrum emerging because part of the spectrum has been absorbed out of that light. So now what we can see here is that if that same white light, the continuous spectrum, is passed through a different gas, because the energy levels are unique, we would absorb different photons of energy. So in this case, the 3 joule photon is absorbed, the 5 joule photon is absorbed, the 6 joule photon is absorbed, the 8 joule photon is absorbed, and so our spectrum that comes out the other side has different energies missing from it, and this allows us to identify different types of gases based on the absorption spectrum. So the spectrum that comes out of the other side is called an absorption spectrum because it started with a continuous spectrum and then had certain frequencies or certain wavelengths absorbed or removed from it by electrons transitioning into a higher state, which left only other energies to go through and gives a unique absorption spectrum for each different element, where a typical absorption spectrum would look something like this. You can see most of the spectrum is preserved, most of the continuous spectrum, but there are dark lines where those specific frequencies have been removed or absorbed out of the light spectrum. You'll also see that there are a large number of lines removed here. That is because there are many possible transitions in any element, and I have only shown for the first 4 energy levels. So once again, an absorption spectrum is formed when a white light with a continuous spectrum is shone through a cold gas. That gas then allows the photons of energy that allow specific energy level transitions to be absorbed out, and then the light that we see coming out of the other side is an absorption spectrum because only the necessary frequencies have been removed from that spectrum. We know that every element has its own unique energy levels, which means that the gaps between the first and third and first and fourth, etc. energy levels differ for every different element. So in the emission spectrum, what we do is we apply a potential difference across a gas of a certain element. And what that does is it causes electrons or a flow of current through that gas. That moving current or those moving electrons then collide with some of the electrons in each gas or in the energy levels, which bumps them up and puts them into an excited state. And we know that once they reach that excited state, it is only a matter of time before that electron drops back down to its original state. When it does that, when it drops back down, we know that it gives off energy in the form of a photon, and that photon has an energy that is either related to a frequency or a wavelength with this equation over here. And so what we can see is that when we apply a potential difference over any gas, the energies that are given off are dependent on the type of element and the gaps in those energy levels. So the first example here, we have element X, where we can see when an electron transitions from the fourth state down to the first, it gives off 8 joules of energy, or an 8 joule photon. It will also give off a 7 joule photon and a 4 joule photon. At the same time, it will give off a 3 joule photon and a 1 joule photon. So we get a very specific set of energies that come off this element, and that is different to the energies that come from this element, which would give us 14 joule photon, an 11 joule photon, a 6 joule photon, an 8 joule photon, a 5, and a 3. So as we can see, we have almost a unique barcode for each element, and each of these photons that comes off, that is in the visible spectrum, is a different color. So what we see here is that we form what's called an emission spectrum, where only some colors are given off dependent on that frequency. And so your emission spectrum would often look something like this. Here you can see we have different elements. First one is hydrogen, helium, neon, sodium, mercury. You can see each element has a unique emission spectrum because of those differences between their energy levels. So once again, what we are doing here is by applying a potential difference across a canister of a gas, we are causing current to flow. That current collides, or the particles or the charges in that current collide with the electrons within each element, and those collisions cause the electrons to move up into an excited state. As they move up an energy level, we know it's only a matter of time before they drop back down to their original state, and when they drop down to that original state, they give off a photon of energy, and that photon of energy is specific to the transition that it undergoes.